let's get you back into it. I hope that your impression of vectors is like mine, that they're pretty intuitive. Three-dimensional vectors are not that different. And how you add and subtract them and do scalar multiples is pretty much what you would expect. So I've created a question. Here are three vectors, A, B, and C, in three-dimensional space. One of the kinds of things you might want to do is a calculation involving various combinations of them. The number 2 is called this 2b is called a scalar product, or just a scalar. And so 2 times b, and that one is 3. So if I was doing A, let's do that one. So it's going to be A plus 2b, take away 3c. I would write it something like this. A is basically untouched. Now, if you want to add 2b, I would add, and then I just double those guys. And then if you want to take away 3c, I would take it away, and I just treble those guys. And now all I'm left with is 1, add A, which is 9, take away 9, I get 0. 0, add -2, then take away 6, gets you -8. And -2, add -2, so that's -4, take away 15 is -19. I'd be comfortable about any normal linear combination of A, B's, and C's would be pretty straightforward, right? If they were trying to be awkward, couldn't they make it 3/4 of this and 5/7 of that? That's about the worst they could do. I can't think of anything else that you could do to add and subtract vectors. Now, this is my version of question B now, when you stick this absolute values looking thing, the 2 vertical lines, what that is the magnitude of this vector. That's what you've been asked to find, right? How long is this vector? And so I would do it in 2 stages. I would find the 2a plus 3c part first. So if you double this guy, you get 2, 0, -4. And you add 3 times this guy, so treble it, you get 9, 6, and 15. And if you add these together, you get 11, 6, and 11. And if you want to get the magnitude, which we do, the magnitude of a vector is its components squared and added. You can actually prove it if you go and do a version of Pythagoras, but I'm not going to. It would be that guy. So 121, add 36, add another 121. That's 242, 272, 278. And that would be the length of it. Technically, you should check it to see if you can simplify it. I'm going through my usual combinations in my head. I don't think it simplifies, so that's probably the final answer. You know, if it simplifies, you know, like square root of 20, you would be expected to call it 2 root 5. That's all I mean. Again, pretty comfortable with those types of calculations. So if I give you 2 or 3 vectors and I say, look, add and subtract them or find the magnitude of some combination, this is the process, right? So let's move on, still on vectors, of course, and find what is called a unit vector. Well, this is what it is. A unit vector to a vector v, right? So a unit vector of the vector v is a vector parallel, oops, that's an L, to v, but whose magnitude, or if you prefer the word length, is 1. So if you can imagine, this is my vector v, the unit vector, let's call it u, would look like that. parallel, but 1 unit long. So there is essentially a formula for finding a unit vector. Unit vector U, starts with a U, unit vector of this guy is 1 over the magnitude of V, vector V. Let's see how that works. Isn't 1 over the magnitude of V just a fraction? It's like a half or a third or 7/9, right? If you take a vector and you multiply it by a number, and it's a positive number, don't you just end up with another vector parallel to the first one, but of a different length? That makes sense? Right. 2V would be a vector twice as long, right? A half V would be a vector half as long as V. Well, won't 1 over V give you a vector whose length is 1 unit? Does that make sense? If you found 1 over the length of vector V, if you found the length of this vector, wouldn't it be 1 unit long? Can you imagine that happening? Okay, let's try it. Suppose V is 3, 4, -12. And I want to find the unit vector. Well, the first thing you do is you find the magnitude of it, which is 3 squared plus 4 squared plus -12 squared. And that ends up being 13. And so the unit vector is 1/13 of V. And it will be 3/13, 4/13, -12/13. That is the unit vector of V. Can you see it's just a multiple of V? 1/13 of it. That makes it parallel, doesn't it? And you can check this, but I bet you if you did find the length of this vector, right, the magnitude, it would be exactly 1 unit long. Who's the only vector in the universe you cannot find a unit vector for it? There's only one vector in the universe. It's impossible to get a unit vector for it.
0 vector?
0 vector. 0 vector is weird in lots of ways. There's just one of its many ways. What is the length of a 0 vector?
0.
0. Yeah, it's an instantaneous point in 3D space. What is the direction of the unit vector?
Could it be any direction?
Right. It's either got none or it's got all of them at the same time. Schrodinger's cat, I guess, right? It might be dead, it might be alive, it might be pointing over here, it might not. You'll never really know. Are we cool with unit vectors? Do you want to see another example, or is that pretty much a plug and chug?
Can we see another example?
Sure. So let's change the letters. Let's do A. Oh, maybe I could actually. It's better if I use homework questions because they tend to be nicer numbers. If I just pick numbers off the top of my head, you end up with the square root of 4007 or something weird. I'd rather not deal with numbers that big if I can avoid it. Just finding a question like that. So we're in 12.2. Click on that. Let's see what we have. Unit vectors, where are you hiding? Okay, there we go. An example of a unit vector would be question 12. And so the vector is A. They're calling it 4i take away j plus 8k. And it's definitely okay to do that It's just my brain doesn't like that notation. So I convert it into that. Just makes my life easier. You don't need to. Well, so to get the unit vector of A, I find its magnitude. So that's 4 squared plus -8, -1 squared, plus an 8 squared. And let's see what that is. 4 squared, basically +1 plus 64. Oh, they are good, aren't they? That's why you pick questions from there. It's a nice number, it's 9. And so the unit vector is going to be 1 over the magnitude times the vector A. In this case, 1/9 of the vector A. And that ends up being 4/9, -1/9, 8/9. There's your unit vector for you. You comfortable with that process? Does it seem relatively get this, then do that? Right. Now, there are going to be some style point issues, so can we pretend that it ended up being this calculation? Just for argument's sake, right? Now, you would do 3 over √3, -1 over √3. I know this isn't strictly accurate, but it's for the process. You might be comfortable with that. Do you think in advanced math as you are, that we would allow that as a good style point answer? What do you think you're going to have to do then?
With the √3 up.
Yeah, so top and bottom √3. So this guy is this fella, and this one is this fella, and this one is this fella. And sometimes you have to do a little bit more. And this is one of those sometimes there is just a little bit more to do. So what would you do here to any of these 3? There's only one that needs fixing. Can you see which one can be fixed?
The
Simplify.
first one you can cancel the 3s.
Okay, so not a biggie, but look out for style points. Do you want to see another unit vector, or are you comfortable with unit vectors now? Are we good? Okay. Then let's show you a question that involves unit vectors, but is not a unit vector. An example of this is going to be question 13. And we're being asked to find a vector in the same direction as 6 to -9, but whose length is 3. So they haven't called it this, but I'm going to call it A. You've got to call it something, right? So find a vector that's in the same direction as A, but whose length is 3. So if you want to visualize what that might look like, can you imagine that's A? And I want to find not a unit vector, because a unit vector would have a length of 1, but I want a vector B so that this distance is 3 units, right? So I want a vector whose length is 3, right, but is parallel to A. And I've said that you're going to use a kind of combination of what we did with unit vectors to do that. So the first thing you're going to do is you're going to find the magnitude of the original vector A. So that's going to be the square root of 6 squared plus 2 squared plus negative 9 squared. Now that'll be a miracle if it comes out nice, but let's see what we get. 6 squared plus 2 squared plus negative 9 squared. Would you believe it? They are good. Aren't they? I mean, come on, that's kind of hard to do, isn't it? To take 3 numbers and still get perfect square. But they're called Pythagorean triples, and that helps. Anyway, we've got these guys. It's 11. But that's this fella. The vector B, because it's in the same direction as A, is going to be a multiple of A, right? So all I need to do is figure out what multiple. It's not going to be 1/11th. 1/11th would get me a unit vector, right? That would get me a magnitude of 1. But if we adapt it a little bit, we'll be able to get a vector whose magnitude is, in this case, 3. So what fraction, what multiple fraction do I use of A to get a vector that is 3 units long rather than 1 or 11 units long?
3
5
over
over
11.
Yes. Does that make sense? Right,
Sorry,
11
that's
because...
on me. I'm just following along with mine.
Oh, are we good with that? 11? And 3 units? If you wanted 5 units, wouldn't it be 5 11ths? If you wanted to be 100 units long, wouldn't it be 100 11ths? You see, the 1/11th gets you the unit vector, and then 3 times that would do it. So I wouldn't write it this way, but couldn't you call it that guy? Does that help you see the 3 unit thing? Right, so all these guys are going to get multiplied by 3 11ths. So that's going to be 18 11ths, 6 11ths, and negative 27 11ths. And we have solved the question, or the answer to this puzzle, which is what vector is in the same direction as the vector A, but whose length is 3. And you could check this, couldn't you? Do that squared plus that squared plus that squared and find the answer, and it would have a length 3, right? You could do the magnitude. Are we good? Right. Yeah. You want to see another one of these, or is one of these is enough? Because actually you only get one homework question, so you don't get a lot of them anyway. Are we good with this one? Do you want to see another one? Okay. If you just go back and watch this one, that's how every other one is going to look if you ever get them. Right. The next kind of questions we're going to look at are applications. And to be able to do these applications, we need to know how to find the X and Y components of a 2-dimensional vector. So what we're about to do is only going to work for 2-dimensional vectors. So the questions that are dealing with are basically starting at 14. I'll do a quick scan. So it's 14. And it's going to be 15 as well. 16 for sure. 17 for sure. And 18 for sure. And the last one's just a silly one. That's nothing to do with that. Okay. So we're going to imagine that we've got a vector. And in these questions, although vectors can be drawn anywhere, in these questions, the vector is going to start at the origin in each case. So let's suppose I have a vector, this guy here, and we'll call the vector V. And I'm going to tell you some information about this vector. The first thing I'm going to tell you is that it makes an angle of theta with the x-axis. And the second thing I'm going to tell you about this vector is its magnitude is 10. Or actually, well, in this case it is 10, but let's just say its magnitude is v. Later on, we'll give you numbers. Then a typical vector v is made up of an x component, right, and a y component. Right? How far in the x direction do you travel, and how far in the y direction? And the formula for it is the magnitude of v cosine of theta and the magnitude of v sine of theta. I know it's a while back, but can you remember trig and doing x equals r cos theta and y equals r sine theta? Remember polar coordinates? X equals r cos theta and y equals r sine theta. The r is the magnitude of the vector, so this is essentially the same equation. So that's basically how you find the component. So let's do an example of what that might look like. Let's suppose we have I'll try and find one. It's always good to do ones that they have. I can't find a decent one. Okay, there's that'll do. So suppose I have the magnitude of this vector is 10. And let's suppose the angle here is 48 degrees. I would like to know what the vector v is. So don't expect nice numbers for some of these questions. If the angle is a standard angle like 30 degrees or 60 degrees, then we'd expect you to get your unit circle and get exact values. But when it's 47 degrees, 17/11 pi, things that don't work well in the unit circle, you just do them to decimals. So it's going to be the magnitude times the cosine of the angle and the magnitude times the sine of the angle. And let's say that they want the answer to 1 decimal place. So make sure that I'm in degrees, which I am right now. And so 10 times the cosine of 48, that gets me 6.7 to 1 decimal place. And 10 times the sine of 48, that gets me 7.4. So to 1 decimal place, a vector, this vector here, this red one, is 6.7 along, right, and 7.4 up. So that's how we would get the components of that. Sometimes they also ask you for the magnitude of that vector. Well, won't that be 6.7 squared plus 7.4 squared? I'll go here. I'll do a square root of 6.7 squared, add 7.4 squared, and I'm getting the answer. Oh, that's nice. Yeah. Basically, to 1 decimal place, isn't the answer 10? 9.98. To 1 decimal place, the 9 rounds up, so it's 10.0. So far, so good. Now, let's suppose that this right at the center, right? I'll draw it over here again. Let's suppose we'll keep some of the numbers the same, right? So right at the center, we have a boat, and there's a tugboat. I'm calling this guy V, and he's pulling at an angle of 48 degrees away from east, and he's pulling it with a force of 10 units, right? Well, we already know what V is. I've calculated that. And then there's a second tugboat, and that second tugboat is over here. And I'm going to call that second tugboat W. And the magnitude of this is 20. And the angle that it makes here is 12 degrees. And we're going to be combining these two vectors together. So can you imagine there's a boat where my pen is, and it's being pulled on the left and the right by tugboats, right? And they're pulling it down the, the estuary. Won't the resultant force, what you get when you add these together, won't it be a combination of V plus W? And it might end up pointing that way, right? And the reason why I think it's going to point more to the left than to the right is, isn't this a much bigger force than that? And isn't this a much sharper angle, right? So there's a bigger tendency. So what we're going to do is we're going to find what the resultant force, that's just a fancy name for what you get when you add vectors together, right? Now, that means I have to find out who he is. I already got that one. So what do I know about the vector W? Well, it's going to be 20 times, and I'm not writing the angle down here for a second because there's a mistake you could make, and 20 times the sine of the angle. Now, the mistake you could easily make is that you put 12 degrees here and here, but that's actually not the angle theta. The angle theta is always measured from the positive x-axis going in an anti-clockwise direction. What is the real size of this angle for the vector W? It is actually not 12 degrees. What's the real size?
168.
And what you did there is you took it away from 180, didn't you? Can you see that if you just look at the numbers, you could quite easily put in 12 there, thinking, I see 12, I use 12. Now on a calculator, again, this is a bit messy, so bear with me. I'm going to do 20 times the cosine of 168, which is negative 19.6, and 20 times the sine of 168 is 4.2. Are you comfortable that that negative 19.6 actually makes sense here? In the x direction, aren't you going roughly negative 19 units this way? Right? Negative 19 and then going up 4.2. So that's exactly what I would expect. So far, so good. Now, what would the resultant force be? Well, you would do the two tugboats vectors added together. And so in this case, it would be 6.7 and 7.4 added to negative 19.6, 4.2. And that's probably better done in a calculator for safety. So 6.7 in that guy gives me a negative number of 12.9. And this guy gives me a positive number of 11.6. So if I was making a guesstimate, it would probably be roughly in that green dotted line direction. Does that make sense? It did pull it more to the left than to the right. So if you're only being asked what is the resultant vector, it's this fella. What else might they ask you? Well, they might ask you for the resultant force, and they might ask you for the angle it makes with the x-axis, essentially asking you for theta. Well, the resultant force is just another word for the magnitude. The length of a vector in these stories represents force. Long vectors, big force. Little baby vectors, almost no force at all. So the resultant force is negative 12.9 squared, add 11.6 squared. And again, I'll do this to 1 decimal place. Do you know, I feel like an engineer today and I don't like it. But anyway, keep going. Negative 12.9 squared plus 11.6 squared. I must have done something weird here. Probably need a bracket there. Okay, what did I do weird? Oh, I think I know. Okay, I give up. What on earth is wrong with that calculation?
Too many end brackets, not enough beginning brackets.
The joys of keeping track of brackets, right? But we kind of figured them out. So the resultant force is about 7.3 newtons, or whatever the units happen to be, foot-pounds, something like that. And last but not least is that we need to find that angle. Okay, I'm putting you in this spot here because I know it's a long time since you have done trig. Can anybody remember the formula for getting the angle theta? And it starts with the tan of theta equals something. Can you remember what it was?
Isn't it opposite over adjacent?
Good. Now, instead of the word opposite and adjacent, could you do that in terms of x components and y components, and you're there? You did good to get that far. Okay.
So, no, I don't think I can.
Opposite would be y.
Correct. So y component over x component, right? Same formula, but things get called different things, right? In this case, the opposite and the adjacent are called y components and x components. In this case here, then, won't theta be the inverse tan of that fraction? So I'm going to go inverse tan of 11.6 divided by negative 12.9, and do not be surprised about the weird answer, because negatives very often give weird answers. So the inverse tan of 11.6 divided by negative 12.9 is negative 41.96, which, if I'm rounding off to, we get that. But that is definitely not the right answer. That guy is down here. Isn't that what negative 42 degrees looks like? Would you agree that the angle I want is in the second quadrant? I'm not looking for the angle in the fourth quadrant. It might be in a different world. I'm looking for the one where my pen is, right? I want to know that angle. Well, that would be closer to the one I want. So if you do a little imaginary dotted line here, won't that angle also be 42 degrees because of the symmetry? And so after all that hard work, you take away 42 from 180 and you get 138 degrees. Do you see how that is a bit quirky? Right? You've got to bring pre-calc 2 stuff, trig stuff, to the party. Now, one day in the future, you're going to have a calculator that tells you the 2 answers to any inverse trig function. You know, if you find the inverse sine of something, there's 2 answers. There's the one the calculator gives you, and then there's the other one. And half the time, the one the calculator gives you is the one you want, and half the time, it's the other one. And you see, in this case, it was the other one. So you just have to be aware of that. Are we cool? And that is how to find the resultant force, which was 17.3 units, and the angle for theta, that big angle there, would be 138. And if you look at the picture, doesn't that seem reasonable, right? It's 100 and something anyway. Let's try another one. And this time, this is question 17. And you've got a vector, or a force, I probably should call it, going this way. And the angle is 45 degrees. And you've got another one pulling down the way. And its angle is 30 degrees. I'll call this vector, I know, I'll call it A and B just to be different. And we're told that this vector has a magnitude of, say, 10 pounds. And this one, a magnitude of 14 pounds. So what you're really telling me when you say that is that the magnitude of A is 10 and the magnitude of B is 14. Right, so when they tell you a force, think of that as them just telling me the magnitude of the vector, how long it is. And we are going to be asked, very similar to this question I did a few minutes ago, we're going to be asked to find the resultant force, what you get when you add these together, right? And secondly, we're going to be calculating what angle that resultant force is. Now I'm looking at this guy and, I don't know, if you were a gambling person, do you think the resultant force is going to be a little below the x-axis, or do you think it might be a little bit above the x-axis? What's your gut feeling? I'm guessing as well, so don't worry about it. So you're guessing as well. What do you think the resultant force? Bang, oh, it could, I guess it could be bang on the x-axis, couldn't it, as well? But it's probably, I'm guessing, just pointing a little bit above the x-axis, right? Just pushing it a little bit higher. And the only reason I'm saying that is that this angle is a lot bigger than that angle, but this isn't, although it's bigger, it's not a lot bigger. So we shall see. So for the vector A, it's going to be the magnitude of A times the cosine of theta, and the magnitude of A times the sine of theta. And these are all going to be decimals, even although these are nice numbers. I'm going to do 10 times the cosine of 45 degrees. And I'm going to do 10 times, almost did it wrong again, sine 45 degrees. And to one decimal place, because I don't want to do too many buttons, it's going to be 10 times cosine of 45, which is about 7.1, and the other one is also 7.1. Are you comfortable about the components of vector A then based on the angle 45 and a magnitude of 10. So far, so good. Right, let's do B then. The
Mr.
other.
Person,
Yes.
on the drawing, is that the 30? Would it be negative? And
Oh,
if
this one here?
the 30 degrees is not negative, is that going to affect the outcome?
It is. Let's see how it's going to affect it.
Okay.
It's going to be the magnitude of B, cosine of the angle, the magnitude of B, sine the angle. And just like the other one, aren't angles measured from the positive x-axis going anti-clockwise to here? So what you were saying, if I picked it up correctly, was will that be negative 30 degrees? Actually, that would be okay, but I think it's better to always measure the angles the same way. So what angle is that 30 degrees really going to be as far as theta is concerned, right? It's not going to be negative 30, isn't it going to be plus 330? You all comfortable with the way you measure the angle from the positive x-axis going anti-clockwise? So this time it's going to be 14 times the cosine of 330 degrees and 14 times the sine of 330 degrees. And if I do this correctly, shouldn't the x be a positive one and the y be a negative thing? Would you agree? Positive down negative. So I want this to be positive and I want this to be negative. Let's see what we get. 14 times the cosine of 330 is 12.1 and it's positive. And 14 times the sine of 330 is negative 7, exactly as predicted. So we're being asked to find the magnitude, the resultant force, right? So that's what you get when you add these two together. So the first vector is 7.1, 7.1, and the second vector is 12.1, negative 7. And that gets me 19.2, 0.1. Am I good or am I good? Isn't that just a tiny bit up the way, right? 19 and a bit along and a 0.1 up. It's almost Jewish, isn't it? So that is the resultant force. The magnitude of that resultant force is the length of this vector. And I'll try and keep all
I
my
have a
brackets.
question.
Yes.
So when we're doing these in the homework, should we be keeping it as the square root of 2's and keeping it as the exact?
No, these questions just, it's engineers, remember, they don't know square root of 2's. So you're going to do 1.414. The questions also say to 2 decimal places or to 4 decimal places. So the minute you see that phrase, you know you don't need to keep things exact. If it was just find the magnitude and they never mentioned decimal places, then you would have to live with all these ugly square roots that you tend to get when you do exact values, but not in these cases. I doubt very much if that's going to be a nice number, so it's going to get rounded off as well. So it's 19.2 squared, add 0.1 squared, and the answer I get is 19.2, right? And if you want to find the angle, which they do, and how do they, oh, they just call it the word angle, right? Okay. So if you want to find the angle theta, it's going to be the inverse tan of the y component divided by the x component. So in this case, it's going to be the inverse tan of the y component divided by the x component. And on our calculators then, inverse tan of 0.1 divided by 19.2, I am looking at 0.3. Wow. 0.3 degrees. Right? It's hard, isn't it, almost bang on the x-axis, right? So if that was a boat and these were two tugboats, wouldn't this combination be pulling the boat virtually exactly due east, right? 0.3 degrees, almost perfectly. Now I've only done 2, but do you know you could do 4 vectors? Wouldn't you just do the same thing 4 times and then add the 4 of them together? Right. So the process doesn't change when there's more than one vector. So if I had a third vector down here, wouldn't I just find its components, call it vector C? This would become A plus B plus C, and you get the answer. Then you could get the magnitude of this, then you could find the angle, right? So if you know how to do it with 2 forces, you can do it with 3 or 4 or 5 forces. How are we doing, guys? Did you know you were coming to an engineer class? Some of you are probably, actually, I'm thinking, and I'm not good at thinking, but I'm thinking, yeah. Is this the kind of thing some of you have already done in other classes? Have any of you done this kind of stuff somewhere else?
More or less.
Yeah, I've done this in physics.
Right. The way I do it, is it close enough, or is it kind of, yeah, you don't do it the way we do it, or at least you don't use the words that we use?
It's actually much more clear.
Oh, thank you. I guess it's
Yeah, I would
because I'm
agree.
not good at engineering. I have to be slow to make sure I get it right. Was a nice compliment. I'm going to tell my wife I get complimented today. I'll get a big head. Right. This one I'm not going to do completely, but I just want to talk about it so we can get it out of the way. So in this story, you've got a vector pointing up this way, and its magnitude is 100 newtons, and the angle here is 60 degrees. And you've got another one, this green one, going this way, and it's 400 newtons as its magnitude, right? And there's no indication of the angle. This guy here, the guy that I'm going to call A, and this other one, I'm just going to call it B. You can pick any letters that you like, because when you write it down in WebAssign, you don't tell me A plus B, you just tell me the numbers, right? So you can call it anything you like. To get A, isn't it going to be 100 magnitude times the cosine of 60 degrees, comma, 100 times the sine of 60 degrees. I do not need any calculation at all, which is why I kind of wanted to do this one before we left. I know exactly the components of vector B just because I can see it in the picture. What are they?
Negative 400, 0.
Does that make sense? Now, if I wanted to do a formula, wouldn't it be the cosine of 180 and the sine of 180? And it would get you these two. Right, can you imagine, we haven't time, but couldn't we add these together and get the resultant force? Couldn't we find the magnitude of it, which would be the magnitude of the force, which I believe is 360.6 according to the thing over here. And then don't we do the inverse tan of y component over x component to get the theta? And if you're lucky, the theta they give you is the right answer. And if it's not the theta, then it's the wrong answer. So if they told you theta was 166.1 degrees, would you be happy with that answer, right? If the inverse tan said it was that angle, would that be a good answer and you'd be good to go? Just look at the picture. It's 166.1, look reasonable. Right. If the answer was negative 18.9 degrees, would you be worried? Okay, and if you imagine where that number would be, wouldn't it be down here somewhere? So you imagine the dotted line going this way, and that is 18.9. I hope I can't count. There, 12.9, right? Wouldn't you take 12.9 away from 180 and you would get it, right? So when you're doing an inverse tan, either the angle they give you is the one you want, or they'll give you some ugly negative one, which you have to figure out what it is.